Okay, so most of the homework is asking you questions about dimensional consistency. And we talked about this briefly. The dimensional consistency is the idea that both sides of an equation have the same dimensions. An equation that has that property means it's dimensionally consistent. And I'm going to ask you a bunch of questions about whether some equations that we use in environmental science are dimensionally consistent or not. And the way that you're going to be able to answer that question is to show me the derivation where you take the equation I'm asking about, you plug in the dimensions for each of the variables, and then you simplify the dimensions algebraically to show me that the dimensions on the left side simplify to the same dimensions as the right side of the equation. So I want to work an example just to give you an idea of how to do this homework. In this case, we're going to talk about the Darcy Weisbach equation. The Darcy Weisbach equation is a hydraulic equation. It's an equation that tells you something about the influence on the friction of a channel on the depth of the water and the velocity of the water. So a given channel doesn't determine how much water is flowing in a stream, for example. That's determined by the watershed upstream of that point. What you need is an equation that will tell you, well, is it slow-moving deep water or is it fast-moving shallow water? That's what Darcy-Weisbach equation helps us with. So the variables in the Darcy-Weisbach equation are listed here. That U bar is the average velocity of the stream water. G is the acceleration due to gravity. R is the hydraulic radius. S is the slope of the water surface. And F is a dimensionless friction factor. Now, in order to do a dimensional analysis with this equation, we have to know what the dimensionality is of all the variables. So U is an average velocity. We talked about that in terms of the basic equations of Newtonian physics. A velocity, hopefully logically, is going to be a length per time. G is an acceleration due to gravity. Well, acceleration, we talked about that too. That's the change in velocity over time. So that's a length per time per time. Those times can be combined to give you length per time squared. R is a fairly unique to hydraulics variable, and it's defined as the area of the cross-sectional area of the channel divided by the wetted perimeter of the channel. The wetted perimeter of the channel is the length of a line drawn from one wetted edge to the other along the bed. So A, cross-sectional area, hopefully we've got the dimensions of that down now, that's length squared. P is the wetted perimeter, that's just a length. It's a very ununiformly shaped length because it's along the bed of the stream, but it's still just along the line, the given length of that line. So we can think of the hydraulic radius as length squared over length. S is the slope of the water surface, or sometimes what we call the energy slope. That's the vertical distance change over some horizontal distance in the water, in this case longitudinal distance along the channel. So a slope then is going to be a length per length. It's a length of elevation or vertical distance change over a length of a horizontal distance. And finally, that F is the friction factor, and it is a dimensionless number or simply a count. And it characterizes the effects of friction. So a higher F means there's more friction. So those are all the dimensions of the variables. Another thing I'd like you to do on the homework is to get some practice using some sort of tool for making professional-looking equations. At some point, since you're a graduate student, I'm almost certain that you're going to be asked to represent mathematics from your work in a professional manner. And at some point, you need to get used to using some sort of equation editor tool. Now, I don't care which equation editor tool that you use. You're welcome to use any, but there is one with Word, and the one that comes with Word has gotten a lot nicer over the years. In fact, it's got a lot of shortcuts where I've gotten to the point where I do all my math in Word in terms of derivations. It's just become easier for me to do it that way, and in the long run takes me less time because it's easier for me to fix mistakes when I'm on a computer than I am working with a piece of paper. So what I'd like to do is bring up Word here. And I'd just like to give you a quick rundown on how to use Microsoft Word's equation editor and some of the shortcuts that make it very easy to use. That once you get the hang of it, you can do math extremely fast in Word. And I'd like to give you some tips on how to do that. So first of all, in order to insert a new equation, there's a lot of things you can do with the equation editor just using the ribbon bar and the menus up here. So one way to insert a new equation is to go to Insert, and over here on the right you should find an equation icon. And if you click on that, it will give you an equation editing box and tell you to start typing the equation within that box. So that's one way to do it, but again, there are several hotkeys or key sequences that you can use to make using the equation editor much faster. And one of those is to hold down the Alt key and hit equals. This is on a Windows machine. Unfortunately, this tutorial is not going to be very good on a Mac, but I think that there are equivalent hotkeys on a Mac that you can look up. So if you've got your equation started, you can start typing in variables, or start typing in, just typing in the math in terms of using the keyboard. So, we've got this variable u in Darcy's law that is the average velocity, the variable for average velocity. And note that it will automatically put things in italics because, like I said, in formal mathematical notation, all variables are going to be in italics. But we also, for that u, we want to put a bar on it because we used u bar for the average velocity. That's the discharge over the cross-sectional area, the average velocity. So there's a quick way to start putting decorations in. Now there are a lot of sequences in Microsoft Equation Editor that start with a backslash to indicate a particular character you want to put in. In this case, we want to add a bar, so we can type a backslash and bar. Now if I do that and I hit the space key, the space key is a key for Microsoft Equation Editor to say, I want to try to interpret that. So if I hit space, it'll actually turn that slash bar into a bar. And this bar, I want to be a decorator on top of a variable. So if I hit space again, it will turn the bar into a bar that's over some place that I can put some other text. Like I can type anything here. And it would put it under the bar. But what I want to be under the bar is a capital U. So then I'm going to hit the right arrow key, so I'm no longer under the bar anymore. I can, go back and add stuff under the bar if I wanted to, but I don't want to be under the bar anymore. So if I hit the right arrow key, you can see the gray went away, which means I'm now starting to the right of where I was. Now I need an equal sign because Darcy Weisbach is characterizing that velocity by a term on the right side. Again, there's a keyword with a backslash, SQRT, that gives you the square root operator. And again, if I hit space again, I'll have that square root operator, and I'll be able to backspace or hit the left arrow key to put stuff underneath that square root. Now there's more than one way to do fractions, but I know I want a fraction in the square root. So one of the quick ways to get a fraction going is just to hit the forward slash and hit the space bar. And as soon as I hit the space bar again, it tries to interpret that forward slash, says, oh, he wants to create a fraction. I'm going to create a fraction with the ability to put more stuff in the top and the bottom. That's those dashed boxes. And then I can just use my arrow keys to get back to the first box, and this is what goes in the numerator. Darcy Weisbach, this should be an 8, G, capital R for hydraulic radius, and S for energy slope. And in the denominator is that friction factor F. Now I can do a lot of those things just using the button bar up here, or the ribbon bar up here. And I can find all kinds of special characters to put in there. I can get a much longer list of special characters. I can put in fraction notations. I can put in various superscripts and subscripts. So you can do all of this by hunting things down and clicking on them. But if you get good with these hotkeys, it goes a lot faster. So if you end up doing a whole lot of math, it's worth your time to learn how to do that. Okay, so I have this equation, and I want to do a dimensional analysis of this equation. So I don't really want to start over. I just want to plug in different values. So I'm going to highlight this equation, and I'm going to put it on a long line, on a new line. And now I can go ahead and start plugging in the dimensions of these variables and then start doing some algebra to see how it goes. So this u bar, if you remember, that's a velocity, right? So I know that should be a length per time. So I'm going to overwrite this u bar. If I want to put in square brackets, I can put in a left and a right square bracket, and I hit space. Again, it'll put in those square brackets. Then I can arrow back to fill in the stuff inside that those square brackets. That's equivalent to me going up to the design for equation, going to brackets, and picking the square brackets. Now I want a length per time here, so I'm going to put an L, T. Now here's how you can do a superscript very quickly. The caret, up caret character, that's Shift 6 on most keyboards, is going to allow you to create a superscript. Again, I put that character in, I hit the space bar, it automatically creates a space to put superscript. In this case, I want a -1 in there for length per time. Now there's something wrong with this, right? Remember, no italics for dimensions. So I need to get rid of the default italics in Equation Editor. A quick and easy way to do that is to change the font. One way to change the font is to go back to the home ribbon bar, and there's a way to turn italics on and off. So there's a quick way to change the length per time there into non-italicized font. Now we can go through. That 8 is just a number. It's a count. So we know that's going to be a 1 in square brackets. So I'm going to create the square brackets, arrow back, put the 1 in there. How about that G? That is the acceleration of gravity. Can we remember what acceleration is? Length per time squared. So in place of the G, I'm going to copy and paste this because it's mostly what I want. Length per time. I just need to get rid of that 1 and make it a 2, length per time squared. Hydraulic radius, that is the cross-sectional area of the channel divided by the wetted perimeter. That's L squared over L. So again, now I'm going to want to insert a fraction in the middle here. If I were to just put a fraction here and hit space, it would actually try to turn everything to the left. But I don't want that, and there's a way to get around that. If I just put a space here and then the fraction, the slash, then it'll create a new fraction instead. And I want to put, this needs to be an area or length squared. Get rid of my italics. Divided by length. Get rid of my italics. So that is hydraulic radius, right? I replace the hydraulic radius with those dimensions. And finally, the slope. Well, that's length over length. I'm going to go ahead and let those divide out because I know that needs to end up being dimensionless. So we'll call that 1. And finally, the friction factor, that is a dimensionless coefficient. So that is also going to be a 1. Now another way to show the square root is to use exponents. And since we're using exponents for everything else, I'm going to go ahead and put in parentheses here. I'm going to do a superscript. I'm going to do a fraction in the superscript. And I'm going to take that to the half power. And then instead of using the square root symbol to be consistent with my exponents and my dimensions, I'm going to use the square root. So this is just a quick demonstration of manipulating an equation. Okay, So that's the Darcy Weisbach dimensional analysis with all of the fundamental dimensions for each variable filled in. Then it's just a matter of doing some algebra to show how the two sides simplify to the same dimensions. Let's see if that works out. So if we're going to show the derivation, we don't want to just start editing this. We want to show how the derivation progresses, right? Now the first thing that we can do is recognize that these ones, all of these ones, are not going to affect these calculations. They're not going to have any effect on the dimensions. They're just ones. So I can delete the numerator and I can replace this with just that. And then we can see from here to here that we've gotten rid of the ones. Now we can start simplifying our L's and T's that are inside the square root here, or inside the half power. We have length per time squared. This length squared, and the length will divide out to a length. That will combine with this length, and you'll end up with a simplified length squared per time squared. You can always look back to the previous step to remind yourself length squared over length. Yes, that's length times this length, length squared over time squared. And then I've got length squared per time squared. The square root of that, you just need to square each of the terms, take the square root of each of the terms using your understanding of the algebra of exponents. So we can show step by step how this, cut and paste the L over the exponent, cut and paste the T, whoops, over the exponent. Oops, didn't want to do that. I just need to change the exponent to 1. There we go, t to the minus 1. So you can show step by step the simplification of how we can demonstrate the dimensional consistency of the Darcy Weisbach equation. So the answer to this question is yes. This equation is dimensionally consistent, which means that any sort of consistent application of units for all the variables are going to work and are going to give you valid units for velocity. They may be strange units, but they'll be valid. And these dimensionally consistent equations, as we mentioned, they tend to be those that are derived from more fundamental theory, as opposed to just looking at patterns in data and finding a mathematical equation that works. There's a reason that things are in the numerator and denominator, and that's definitely true of Darcy Weisbach equation in terms of its derivation from theory.